So I've got a trigonometric integral here. I've got square root of tangent theta divided by sine theta plus cosine theta squared d theta, and the parameters are from 0 to pi over 2. Now, what am I going to do here? It's looking like a u substitution is going to go in there somewhere, and there's going to be some sort of trig identity, I'm assuming. Now, we're looking at the denominator here. Let's have a look at that. So sine theta plus cosine theta, and then square that. Now that is going to give me sine squared theta plus cosine squared theta. That's those two multiplied together. And then I'm going to have on top of that a 2 sine theta cosine theta. Now that's all well and good. Now we want something to work here, obviously, with the u substitution. Just looking at this numerator, we got tangent in there. Obviously sine and cosine are involved there. Now here we got an identity here. That could be 1. And they got 1 plus 2 sine theta cosine theta. So that's still the same as what we've got. But there's also another identity here using the sum rule for sine. We've also got 1 plus sine of 2 theta. So that's the bits we've got there for our denominator just by expanding it out. We've not done anything yet, we just had a look at some algebra. Now, sine of 2 theta, well, straight away I'm not looking very happy with that. Tangent theta doesn't seem to work with that very well. I've got sine theta cosine theta. That's got possibilities. And obviously I've got the first line here, so that all three there are looking okay, but this last one, I think I can definitely reject that one. So a u substitution in my denominator is not going to work when I look at the tangent theta in the numerator. So I'm definitely going to need to u sub the tangent theta. So let's just go with that and see where that takes us. So if u equals tangent theta, normal business when doing u substitution, take the derivative of this, gives us secant squared theta d theta, and then let's get the d theta on its own because we need to replace that. So then d theta, that will give me du over secant squared theta. Okay, now secant squared theta, we know that is 1 over cosine squared theta. So what I could do, if that's a reciprocal of 1 over cosine squared theta, I could also write d theta as cosine squared theta du. So that would be my substitution in there. So if I've got cosine squared theta here, I need to make a cosine squared theta appear in here somewhere so I can cancel it out, because obviously cosine squared theta will not be allowed into the du integral. So cosine squared theta might work with this, but I'm still left with the sine. So I can now eliminate that one. So the only one I'm left with is this one. Now I've got sine squared, cosine squared, 2 sine theta, cosine theta. So let's just put that in my denominator with the u substitution and make a start on that, and let's see where that takes us. So let's take this off the board. Okay, so now I've got all that in there, and I've got all this stuff here which is not invited into the u integral. So I've got to do something with all of this. And you'll notice here my parameters of integration I've not filled in yet. So first of all, let's do the easy bit. Let's look at the parameters. So let's plug in 0 for theta. So if u equals tangent of 0, so just a 0, not theta, u equals tangent 0, that's 0. So my lower bound stays the same. Let's have a look at the upper bound. So u equals tangent pi over 2. Well, tangent of pi over 2 is technically undefined, but tangent of pi over 2 we know is the limit approaches pi over, or limit of the theta approaches pi over 2, we know it approaches infinity. So this I can replace with infinity for my upper bound. So that's taken care of in the u substitution. Now what about this? Got cosine squared theta in the numerator. Denominator, I've got all this stuff here. What about if I had a cosine squared theta, got some sort of factorisation of cosine squared theta, and then I'll be left with something else. Let's see where that takes us. So let's pull this bit here, this fraction, down here, and let's just work on that. So I've got cosine squared theta. I want to take out cosine squared theta to get it to cancel. So let's factor out cosine squared theta. So basically I've got to divide all of these by cosine squared theta. And then that's what I can put inside the brackets for a factorisation. Well, some of these are looking pretty straightforward. I mean, this one straight away, that's a 1. This one is tangent squared theta. So that's looking very promising. So that's done, that's done. What about this one? Well, I've got 2 sine theta, cosine theta divided by cosine squared theta. That cosine theta can rub out and I'm just left with cosine theta. So then I've got plus 2 sine theta cosine theta. Well, that's just 2 tangent theta. So now I've got cosine squared theta, 1 plus tangent squared theta, that works, and 2 tangent theta. Now, in terms of my u sub, this is going to work well here for this part inside the brackets, because this bit here will now just be cosine squared theta multiplied by 1 plus u squared, tangent theta is u, so it's u squared plus 2u. And that's looking even more promising because now I know if I write u plus 1 squared, I will get that. So I've now got cosine squared theta, u plus 1 squared. And that will then take care of my integrand with that inside it. So let's put that into the denominator because we've just shown now that all of that can just come down to that. So let's do that. Okay, so now that's the input there we just worked out. So now I can cancel out these cosine squared thetas. So that's all pretty good. Now, integral left there, instead of having this square root, I'm going to write u to the half. I always prefer that one at integrating. So u to the half, and then u plus 1 squared. Now, if I square this out, sorry, if I FOIL this out and square all u plus 1, I'll end up with u squared plus 2u plus 1. Then that's not going to work. Then if I do a u substitution where I let u plus 1 equal another variable, then I'll have square root of some variable minus 1 in the numerator over a variable just squared. Now if I do that from 0 to infinity, that's going to cause me all kinds of problems, especially with the 0. So that's not going to work. But if I look carefully at this, I've got here something that looks like Euler's first integral, which is the beta function. So let's just have a look at that and see if there's something we can do there. And if we can do that, that could save us a lot of hassle. So the beta function, Euler's first integral of that representation is from 0 to infinity. So that works. And then what you have is, so some variable, so we'll stick with u as my integrating variable. So u to the power of a minus 1. So a is a parameter of the beta function. And on my denominator, I've got 1 plus u to the power of a plus b. B is another parameter. Now, the beta function is used a lot in statistics, and they'd be your 2 parameters, a and b. And then that's obviously integrated to du. So the beta function is noted down as b beta a comma b. And a and b are your parameters. Now this has a value. So if I just put my hours down here, to calculate this, we use these parameters. So we ignore the u, that's just like a dummy variable. And that's calculated using the gamma function. So the gamma function of a, gamma function of b, and then we divide that by the gamma function at a plus b. So if we can get this to look something like this, which looks like possible, we can then just go straight to this and get our result. So let's just have a look at that. So we want a minus 1 to be a half. So a minus 1, let's just write that properly, equals a half. Then a has got to be 3 over 2. So that works all good. And here we've got u plus 1, 2. Well, 1 plus u, same really, doesn't matter which way round. So a plus b must equal 2. So if a plus b equals 2, and we want a to be 3 over 2, so 3 over 2 plus b equals 2, therefore b must be a half. So let's rewrite this now into the beta function or Euler's first integral kind of format. So we've got 0 to infinity, u to the a minus 1, so that's 3 over 2 minus 1. So u to the 3 over 2 minus 1, that's still going to give us a half, so nothing's changed. It's going to write it the right way round like that. That's just, it doesn't really matter, but that's just nice. And then we've got 3 over 2 and a half. So the power of this is 3 over 2 plus a half. That's all one power. So that gives us 2. Again, same thing. And then we've got our du. So therefore we can now write that in this format. So now we've got gamma of a, which is 3 over 2. We've got gamma of a half. So that's fine. We can work these out. And we've got then gamma of 3 over 2 plus a half, which is gamma of 2. So we need to work out what that is. So gamma of 3 over 2. Well, if you check the link below, I've done some videos on these gamma function calculations. So gamma of 3 over 2, that's quite a famous result. That is square root of pi over 2. Gamma of half is actually larger than gamma of 3 over 2. So that's gamma of 1/2. That is just square root of pi. So it's twice the size of 3 over 2. And then gamma of 2, well, when you've got an integer, gamma of 2 is just the same as 2 minus 1 factorial, which is 1 factorial, which is just 1. So let's substitute those values into here. So we've got square root of pi over 2. Let's make a bit of space. Then we've got to multiply by that gamma of a half, which is square root of pi. And then divide that by gamma of 2, which is just 1. And then that nice easy result at the end, square root of pi times square root of pi equals pi. 2 times 1 is 2. And then after all of that, just by spotting the beta function here, we've now got our result of pi over 2. So the answer to that is just pi over 2. And that completes that integral. Okay.